So welcome. This presentation will be about how to use Devicetree to support a lot of different add-on boards for an embedded Linux board. When I came up with the idea for this presentation a few months ago, I absolutely hated Devicetree. It couldn't do anything useful for me, but the past 3 weeks it started doing useful stuff and I actually like it. So the presentation is a bit fractured because I had to remove a lot of slides, so please bear with me. So what started all this was the Beaglebone. It's a small embedded Linux computer powered by an ARM CPU, 700 megahertz, and the main feature is that we expose 104 pins on the expansion connector. And we targeted the device at people wanting to move up from, say, an Arduino or an MSP430 launchpad to something more powerful. Like the Arduino has shields and the MSP430 launchpad has booster packs, we have something called capes, which can be used to expand the functionality. We support up to 4 capes on a Beaglebone. That will get you a stack this big. You can probably go to 5, but we don't know how the signals will react because we have a 32-bit memory bus on there that runs at 100 megahertz, so be careful with stacking too much. To make them discoverable, we added a small 32 kilobyte EEPROM which stores configuration values and identification information. We break out 2 of the address pins for that, so that's also a limitation for the 4 capes. And that's basically what a cape is. I'll give you some examples later on. So we have a lot of different types. We have LCDs, we have Wi-Fi capes, we even have someone controlling a radar array with the capes. A lot of sensors like weather station, Geiger-Müller counters, things like that. People are coming up with really interesting ones. So I picked a few capes that I've been working on for the software support to illustrate what kind of problems we will run into when hacking on the Linux kernel. So one of the more simple capes is the weather station cape. It has just a few I2C sensors hooked up to the I2C bus and an I2C EEPROM. So from a Linux point of view, in your board file, you just register the I2C bus and all your I2C devices, and that's it. The big problem is that you can only register your platform data once. So if you have a Beaglebone with a weather station cape, no problem. If you have a Beaglebone with a weather station cape and some other cape that also uses I2C, one of them loses, or you have to be smart enough and say, well, we know this combination, we'll do combined platform data, but as I stated in the start of the slides, our goal is to have 200 different capes by the end of the year. So encoding every combination thereof is just not going to scale. So even if this is a relatively simple cape, it already shows the problems with a Linux kernel board file. I will explain later about board files and platform data later on. Then we have the DVI plus audio cape, which is one of the simpler ones because the DVI framer is basically a passive chipset. It doesn't require any setup. It just takes the 24-bit pixel data that comes out of the expansion board and just puts it in. So you only have to configure the on-chip frame buffer and that's it. The audio codec, that is the hard part because you have to write support for the audio codec for ALSA, and with ALSA system on chip, you also have to write a driver for the bus. So another simple cape already showing problems. And this is the cape I find the most fun. This is, you can see this in action at the 3D printer at the booth there. It breaks out a few PWM modules for pulse width modulation, can do 100 watts per channel. It has Gpio inputs for the homing on all the axes. It has analog inputs for the temperature sensors. It has an LED you can blink. And the stepper drivers are driven by the microcontroller embedded into the chip called the PRU. And at the bottom you have an I2C EEPROM. So This is also a relatively simple cape, but the complexity is mostly in the firmware driving the stepper drivers. But it works. You can see it printing on the left side. So for LCD capes, it's a bit like the DVI cape, but with the added benefit of a pulse width modulated backlight and a few buttons. So just like with the buttons, just like with I2C, you can only register your buttons once. So if you have more capes with buttons, you lose again. And this one is one of the most difficult capes we had to support. It's the camera interface, which uses what we call the GPMC bus. It's a general purpose memory controller. So we get 16 bits of pixel data at roughly 50 megahertz in. It also has I2C for sensor control, Gpio to sense which way you plugged in the sensor to automatically flip it, and an EEPROM on the sensor board. If you go look at the 3D printer, there's also an LCD on display with the camera attached so you can see it in action. So these are a selection of the capes we've described. So next slide will be about Devicetree. So from devicetree.org, that is how they officially describe it. A data structure describing hardware. So that's all nice, that's a nice idea, but when we itemize it, it's data only. So you cannot say, oh, when I plug in this, I want that to happen. There's no if statement. So it's just pure data. You have, if you want to have smarts, you have to do it in the kernel drivers. It only describes hardware, but then you start running into problems because a few slides back we had this one with the buttons. How do you encode the key codes for that? So the Linux people said in a device tree, if you have buttons, you will encode the Linux key code in there. So that's already a violation of the device tree standard right there with a simple example of just buttons, because apparently no one in the PowerPC community thought of buttons being connected to GPIOs. So this is, it falls down already. You compile a device tree with a separate compiler, and that compiler is extremely strict in checking your device tree. So I spent most time putting in extra semicolons to get it to parse again, because pretty much every Linux developer forgets to put in a semicolon. There's no preprocessor support, so you cannot have nice variables. Just like I said, you have to put in Linux key codes. So instead of in the kernel driver, you would say key power for a power button. In there, you have to say 107 because you have to know the numbers by heart. And there are 0 useful tools available to do it. 2 weeks ago, someone proposed C preprocessor support for the device tree, so you can actually use the useful variables like and magic constants like key power to make writing device tree files a bit easier. But nothing has come of that yet, only proposals. And other people are searching for contractors to make nice GUI tools to process your device tree, but still nothing out there in the wild yet. And even device tree is pretty old already. So a example device tree is this one. Can you guys in the back row see it? So it describes things like what is your CPU, and this is an interesting bit. It describes all your frequency scaling with the combination of the frequency and the voltage. And it goes down to where is your interrupt controller, what type of DMA controller, the memory address, it's compatible with the TI eDMA3, etc., etc. And scrolling down, serial ports. This uses the OMA3 driver at this. So it is very structured. And you can pretty much describe everything. So this is how a device tree looks in the wild. So now we will show side by side an example of GPIO keys with platform data and GPIO keys with Devicetree. So this is how we hooked up the buttons on the LCD. It will be small print. I will narrate it. If you can't read it, it's not really a problem, but it's most likely to show the amount of information needed in both cases. So if you only have one cape attached with one thing, you can do something like this. This is the old style for this board. We have on the top left, we declare the pin mux, so we set all the pins in the right configuration. Below that, we register the platform device with a bunch of boilerplate for it. Then the function on the bottom left is a setup function which sets the pin mux, try to register it, has a return value. And on the right, you have the data structure for the pin. So it has the key code, it has the GPIO number it's hooked up to, is it active low, is it active high, and things like that. So this is relatively simple, but the bottom three functions are just boilerplate. And if you have more than one combination of GPIO keys, you're already lost. So if you stack multiple boards, only one will have working buttons. In the Devicetree world, all the boilerplate is gone. So the top left, we describe the pin mux, which sadly is now a bunch of hexadecimal numbers. And if we go back, we can just say that pin has a GPIO function and mode 7 output. That is now known as 0x37. The data structure for the buttons is pretty much the same, but it is all additive. If you have more buttons, you just add more data structures and they all get added together transparently. So suddenly with Devicetree, you can have as many capes you want with as many buttons as you want, and they will all get added. So that is already the big plus of the Devicetree. You can suddenly have more than one combination of GPIO keys, and it handles that transparently. You don't have to do anything. You just add another entry and it works. So I was really surprised by that, and I discovered this 3 weeks ago and I really love it. Similar thing is with the LEDs. You have to set up the pin mux, you have to register it, etc., etc., and you can only have one combination. So because everybody likes blinking lights, in the current kernel on the Beaglebone, we have hundreds and hundreds of lines of this because we encode every combination of boards with LEDs we know of. So you can plug in multiple boards and all the LEDs start to blink, but not because Linux is nice, but because we copy and pasted a lot of things and together. So that is basically unmaintainable. So in Devicetree, again, all the boilerplate gone, just two things, and they're nice additive again. So all the next slides were deleted. So this is now the main slide. And when switching to Devicetree, a lot of subsystems changed in ARM. Devicetree has been there for years for PowerPC, but it wasn't really used in the way that ARM is using it, because PowerPC got smart and they said, we'll institute a PCI bus, and every hardware on the PCI bus is discoverable, so you don't have to do anything in your Devicetree for that. You just say, I have a PCI bus, you plug in something, Linux discovers it and handles that. On ARM, PCI buses are really not there. Some chips have them, but not most of them. Pretty much everything is not discoverable. So for ARM, we had a lot more drivers we had to put in the Devicetree. GPIO keys being one, the LEDs is another one, SPI things. So a lot of things had to be put in there. And I showed you the pin mux settings where you set up the pins. On the Beaglebone, pretty much every pin broken out by the CPU has 7 different functions. So you have to choose the right function before you can use it. And after choosing the function, you have to choose the direction, input, output, pull up, pull down, receiver enable, slew rate compensation, etc. So a few years ago, pretty much every ARM chip vendor had their own implementation of GPIO and pin muxing drivers. So if you wanted to do something, you had to write a few different drivers. That was made slightly better by something called Gpio lib, which is kind of a library in kernel space where you can just request a Gpio and you have a specific backend for all the chips. And we now have one for pin muxing as well. It's called pin control, and every driver can have a hook in there and say, I need these pins, and it will configure these pins for you when the driver is loaded. So if you have a driver in Devicetree, you say pin control names is something something, and then you make a Devicetree node called something something with all the pin mux in there, and in there you say pin control single, which is the most used drivers, which is basically covers every IP block that uses a single register per pin, and that covers, I think, 80% of all the GPIO and pin control things out there. So that's a good thing that it's now central. And the best thing about pin control is that now that it's centralized, it does resource tracking. In the old 3.2 kernel, you could pin mux one pin one way, and then a few lines later pin mux it the other way. So the frame buffer driver said, I will mux it to frame buffer driver, and then your microcontroller came along and reconfigured a few pins, and if you were unlucky, someone else turned one of the pins into a GPIO. And you had no way of knowing it except for vetting all the drivers. Pin control just prints a message saying, hi, the frame buffer has already claimed the driver, so I'm not going to claim it for the microcontroller or the GPIO. So you get a nice error message, what is happening, and more importantly, who is conflicting. And we found a lot of bugs of that already, and it enables us to support conflicting capes a bit neater. For example, we have a Wi-Fi cape where the Wi-Fi chip is hooked up using SDIO, but MMC data pin 3 is shared with the weather station cape for the one-wire sensor. So with pin control, we can choose if we want to actually use the MMC or use the sensor. So that is not really thanks to Devicetree, but Devicetree spawned the pin control framework. And by doing it with Devicetree nodes, it makes resource tracking a lot easier, because you now have a file where you can easily identify what's going on because it's data only. And what I also like is we have the Beaglebone. Texas Instruments has their official test module, what they call the EVM, the evaluation module, and they want to support it in the same board file. So in the old kernel, we basically, every single step, there was an if statement. If the board is EVM version 1, do this. If it's version 2, do that. Oh, and if it's a Beagleboard, do something completely else. So it was a political solution, and with Devicetree, we can now just say, this is the processor-specific thing, these are all the UARTs, GPIO blocks, etc., and we include that file. It's called the DTSI, Devicetree include, and we can share a lot. So the CPU file describes everything and disables every IP block by default, and in your board file you just say MMC controller 1 status is enabled, or rather status is okay, and you get MMC working. You don't have to know the memory address or anything. It's just a 3-line thing. So we can share a lot now. But now that we have Devicetree, we now have 3 things we need to keep in sync. We have the bootloader, which loads the kernel, and the Devicetree. It used to be the bootloader loads the kernel and boots it. Now the bootloader loads the kernel and the Devicetree. In theory, the kernel and Devicetree are independent because it describes only data. But we've noticed that when silicon vendors write a driver, they do Devicetree integration. They submit it. It gets shot down and ripped to shreds, and they have to redo it, and they do it in a slightly different way. So every iteration of the path set, the Devicetree content changes in an incompatible way. So right now with the 3.7 RC bring up, we are using a so-called appended Dtb, where you take the kernel and then you append the device tree on the end, and the bootloader only loads one file because it's too hard to keep in sync. So what we want to do for the hardware enthusiasts and the hobbyists on the Beaglebone is that they just change the device tree, compile the device tree, and that's it. They don't have to touch the kernel or the kernel source. So we use a separate device tree binary for that. That is the end goal, because that's the easiest. But right now we just cannot do that because it's too darn hard to get right. So that is one of the things that need to be worked on, that people need to pay attention when they're writing drivers so they don't have to change it every other week. And more importantly, you have to go through a few steps, because it has already happened that someone said, oh, but we need to do it differently, but the format is frozen, and then you start running into problems which you cannot really solve cleanly. So everything is nice. You have device tree, it works, it boots, but it turns out that not every driver has device tree bindings, which is what we currently have on the Beaglebone. The analog to digital converters has no device tree bindings, the frame buffer has no device tree bindings. So we had to make a hack. We created a driver called the Cape bus, which is basically a bus driver for the capes. And that add nodes which then instantiate platform data only things. So you can say I have an LCD and it will load the frame buffer for you. It's considered a hack, but it's the best we got. So that is where my big hatred for device tree a few months ago came from. It wasn't device tree that wasn't working, it was just basically all the drivers not having device tree hooks. So for the on-chip peripherals, it's getting better. We're getting more and more device tree support, except for the frame buffer and the ADCs that's being worked on. But a lot of things outside it don't have device tree support. Simple things like I2C centers get an automatic device tree bindings thanks to the I2C subsystem. SPI as well, but other things, no. So people are adding device tree bindings to anything and everything they encounter, and it's not always pretty, because sometimes it just breaks on other platforms. And so for the next year and a half or so, the device tree is not the magic bullet people are hoping for. And then, just like key codes, there are another of other things that are essentially non-hardware but need to be covered in the device tree. And the device tree people saying we're not going to change the standard, and I can agree with that, because it's not only used in Linux, but on the other hand, the hardware has changed. So I don't know what it's going to give, but something has to give. That's the end of my slide. So I'm going to do a question round and then pick up on a related topic if you don't have a lot of questions. So any questions?
Just from general experience, any vendors who are particularly cooperative in the device tree project, or with adding the drivers as opposed to other vendors?
It's not a matter of choice anymore. If you have a new platform, it has to be device tree. You cannot get a new board file based platform in. So for the Beaglebone, we have the AM335X, it's device tree only, the system on chip, so we have no choice. OMAP 5 is the same, and they used to work at Texas Instruments, and OMAP 3 and OMAP 4 were already in and had a board file with platform data that worked, and they started moving to a hybrid model, and a few months ago they said we can fully boot it on device tree and it works and it's so great. And then we discovered that if you have a board file, it will instantiate all the drivers and ignore the device tree for various bits. So when we booted it on the Beaglebone, we said, oh, we have drivers for the memory bus and this and that, and it didn't work. So we made it honor the device tree, and then suddenly OMAP 3 and OMAP 4 broke. So we had to fix that. So companies are cooperative, but it's not by choice. Any other questions?
It's a clarification. Do you make a device tree for the Beaglebone in all possible capes and use that device tree, or do you have to customize the device tree for the capes that you have on your board?
It's a bit of both. I can show you the device tree we have. What we have created is so-called a cape bus with a generic cape. So we added all the different capes and descriptions below. Let me scroll down a bit. Is it TPS? Right, so we have a node for the DVI cape, which the version number for the EEPROM, the bit for the DVI, the LEDs. So for each cape, you have to add such an entry. But you don't have to write a specific driver for the bus for each cape. That's why we have the generic cape. Let me see if I can find that. Yeah, this is the generic cape where you just, well, it's the weather station cape, which has only had the I2C sensor, so this is what you add. And the trick is that you just, in the EEPROM, this is a name, and if you have a device tree node with a name that matches it, it will automatically load it. So you add such a node for your cape which matches the EEPROM, or you add an override and it just works. So yes, you have to add a device tree node for each cape you want, but not a specific driver. I hope that answered your question. Or
you can produce a device tree for the Beaglebone with all 200 possible capes?
Yes.
And then you just plug different capes on it to work?
Yeah, so let me repeat the statement. We produce a device tree file with all the 200 or so capes, and you plug it in and it will automatically match them. So we have a superset device tree, and at runtime the bus driver picks the right node. So that's what the point I was trying to make with what happens if there's an if statement in my board file. You have to put the smarts in the kernel. So that device tree loads it. What device tree does, it loads the I2C EEPROM drivers for us, and the cape bus driver just reads them and then instantiates the nodes through the device tree framework. So we're still using the device tree framework, but we're editing the nodes at runtime. Something called Open Firmware Dynamic. It's a kernel option. It's actually hidden. You need to manually enable it, not through menu config, but editing the kconfig files, but that's what we do. Other questions, clarifications? So let me talk a bit about the cape bus thing we are working on, because we needed, it's kind of a bus, and we want it to be a sort of generic solution for non-discoverable hardware hooked up to expansion ports. For example, the original Beagleboard had an expansion port where you could plug in boards. It only had 30 pins. Panda board doubled it and was kind of compatible. Raspberry Pi has an expansion port, so in theory there is now U-boot support for Raspberry Pi, so we can use Devicetree on it. Kinda. Raspberry Pi is not that open source friendly, but anyway, we can use the cape bus for it. So if you make your Raspberry Pi expansion board, you can use this framework, because every expansion board on embedded is basically the same. You have a few GPIOs, you have I2C, you have SPI, and maybe some of the specific IP blocks like a camera connector, etc. So the idea is that we probably need to name it not KBus, but something different, but that you can just say, these are my I2C devices, I have a one-wire device, or like this, I bought this nifty little 1.8-inch SPI-based TFT from Adafruit, I hooked it up, and it's now a Linux frame buffer. And it's fun hooking up things like that, but people, hobbyists, aren't really kernel hackers. I'm not a kernel hacker, so when someone said, hey, I want to have this display working, I was like, I'm going to ask someone to write a driver for me. And Matt Porter did it as a hobby project, and he wrote a driver for it, and now all you have to do is fill this in, hook up the, 6 or 8 wires, and you have a proper Linux frame buffer that just works transparently on this little 128 by 160 pixels screen. The GNOME desktop looks a bit weird because you have just room for one icon, but it works. It's a standard Linux frame buffer, Python game works, STL works, everything just works. In the Arduino world, Adafruit has written a graphics library for it, but it's not the same as the other graphics libraries for other displays, so one way or another, this is kind of easier to use if you're already used to Linux. For my Arduino world, I'm not entirely sure which is easier, but at least getting it working in Linux is now made a lot easier. And what other things did we have in the KBus? Let me scroll up. It's still a lot of text you have to put in, which is why I was complaining about the lack of tools. So if you design a simple cape and don't want to put in the EEPROM or don't program it, we have an override function where you just basically say one slot in the bus is used by this thing. For example, the Geiger counter cape, it does have an EEPROM, but we used an EEPROM that did have the address pins, but it ignored them. So we couldn't read out the EEPROM, so we had to remove that. So we added an override so you can just say, this cape works. So if for some reason you have mucked the I2C pins as something completely different because you needed, the chip select for the second SPI port, which is shared with I2C. If you needed that, you can just say, I'm not going to use the I2C infrastructure, I'm just going to force this cape or expansion board. So it's not as nice, but we have accounted for that in the framework that sometimes you need to hard code it if you can discover it. And for things like USB and PCI or SATA, that's discoverable, so we don't need to cover that. And here you can see what I meant with pin control. You have pin control names and the things, and then you just scroll up, and you get all these pin control statements for the pin muxing. So what we're trying to do within the Beagleboard and TI team is that if you encounter such a section which is just a bunch of hexadecimal numbers, you add a comment at the end what it actually means. So here we say 0x45 is 54 0x7. That's the memory bus A5 pin muxed as Gpio 121 as an output. So when you start reading through it, you know what it does to make it easier. What we're actually hoping for is just a small tool where you can just say that pin on an expansion connector, that function, input or etc., and then it will generate the Devicetree for that. That's not complete yet. We have the tooling to just click it on a web page and it will generate the pin control fragment for you, but not the complete Devicetree. And what else? So in the top you can see we inherit the system on chip, and this is another include, and in the Beaglebone itself it's just this. So you include it, and I just noticed I made a mistake because I have put a second MMC node in here. That was just a hack to get the extra SD card cape working. It isn't supposed to be in here, but that basically means if you have custom hardware, for example, I make a Beaglebone and I add an eMMC thing to it, this is all you need to get kernel support for it. So this is 6, 7, 8 lines of code, and that's your complete board port. Compared to the big board file you used to have, I think we're up to almost 3,000 or 4,000 lines in just the board file for the Beaglebone to support all the different capes and the different things. And customers hate it. And now you have 8 lines of code and your board just works. And this also shows you don't need to know the memory address for the controller. You just say status is OK. That enables the IP block. And then you add the other things like TI non-removable. It's an eMMC. It's not a slot. It's just a chip. So it's non-removable. So we don't want to have eject commandos or card detect signals. 4-bit bus. And the vMMC supply is basically the power supply for it, which is LDO3. That's a bit of hardware specific knowledge, but if you design a board, that's easy to see. And that's all you need to make a custom spin for Beaglebone plus MMC. I did it also in regular platform data code, and it was awful. You just suffocate in all the boilerplate. So at this point, any questions, remarks, need for clarifications? No. Let's continue. Common. And you can see it goes on and on about pin control. LEDs. Oh, right. That's one of the other problems we ran into. If you register an I2C EEPROM with Linux platform data, you get an accessor function. So basically, when you load the driver, you can read the EEPROM and do things with it. That's usually used to encode MAC addresses for Ethernet controllers and things like that. And in the old 3.2 kernel, we used that to read out the IDs and go through all the functions to set up everything we needed for the capes. In Devicetree, it's data only, so you don't get access to such an accessor function. So we had to edit this driver to expose the accessor function outside of the non-Devicetree probe method. So we're still not sure if it's getting accepted, but we submitted it upstream. And if it gets accepted, it means you can now easily read out the EEPROM in the kernel outside of the non-Devicetree probe function. So I said, why isn't there an accessor function? And I asked it just like that, and the response was, set your MAC address in the bootloader. I'm not even talking about MAC addresses, but that shows that they got this question 1,000 of times, and always it boiled down to, we want to set our MAC address. And in this case, we have what I call non-discoverable hardware with an EEPROM attached to it to read it. So hopefully with that use case, we can get it accepted into the kernel, but it might all fall down. But it's a 4-line patch, so we can carry it externally. And one thing I don't know what happens is we set the clock frequency at 100 kilohertz here. I don't know what happens if you have other nodes specifying other frequencies, what wins. So I think this is a bit uncharted territory. And when I asked around about it during another conference, the general remark was, don't do that. These are all standard regulators, which you need to know for your board. But we've noticed that people just pick up a reference design, either the silicon vendor evaluation module or something like a Beagle, because it's open source hardware. So this is all copy and paste work or include work. And yeah, another thing to keep in mind is that on embedded systems, pretty much every block on itself can be powered down. So sometimes when you try to load a driver, you get weird errors. Usually it says line fetch abort, which in 90% of the cases means you're trying to access memory of a device which is turned off. And you need to manually turn it on. So in the Devicetree world, that's done for you with the status is okay, because it knows about all the dependencies and it will power on devices for you. In the platform data file, you had to pay attention that you first enabled the power and the clocks to the device before you started using it. That leads to funny situations with GPU drivers, for instance. What Devicetree does lack is if I have an SPI device and I register it, it will work, but it doesn't know any dependencies of it. It knows that it's in the SPI block, but if I say I want to have an SPI slave active, it won't do anything to the master. So we added another patch that does recursive enabling of the platform stuff in the Devicetree. So if you say I have a SPI device or I2C device, it will just go up the chain and enable the things for you. That's not a thing we need to submit for review, but we're hopeful that it just works because it saves a lot of time, because our target is still hobbyists, not kernel hackers. And what we noticed, for example, the Geiger counter cape, it generates a few pulses per minute depending on how radioactive it is. So this is one of the few things we did have to write a driver for. So we hooked it to a Gpio interrupt, and every time there's a pulse, we activate a counter, and that works quite well. Actually, it's not interrupt driven, it's polled. So we kind of made a design decision that it will detect radioactive materials to highly radioactive materials, but if you stay close to a reactor, the poll loop is too slow, but in that case you will already be dead. So that's why we didn't go to the trouble to redesigning the board to hook it up to an interrupt. But this shows that even for a simple thing like count pulses, you're forced to write a kernel driver because Linux user space is just not real time enough to read high frequency data. So that's a bit of a downside, but luckily we used the Geiger cape as an example, so the person who designed the cape did not have to write the driver. And because we were already there in a kernel driver, we added an LED subsystem trigger for it. So every time there is a pulse count, you can automatically light up one or more LEDs from the kernel space. So that saves writing another bit of user space stack. And we wrote a driver to automatically convert the analog value to the sense for the voltage boosters, because it's high voltage stuff and we needed to monitor it. One of the things is the PWM pin comes up standard as a GPIO as high, and if you do that you will overheat the MOSFET and the board will burst into fire. So that's why we have vSense to monitor it and try to shut it down from software. New spin will probably have a hardware workaround for that, but yeah. And I've run out of things to talk about the capes and cape. So if you don't have any more questions? No? Thank you for listening. This was my presentation.